Hey everybody, welcome back. Here we're going to look at Unit 7, Conservation of Energy, and then how our energy is going to change when objects collide. Now this is going to build off of our previous unit of work, power, and energy, where now we're going to focus on those specific types of energy and see how that energy is carried from one type to another to conserve the overall amount of mechanical energy that is present in a system. So we begin by just reviewing our kinetic energy. So recall, this is the requirement that an object has to be in motion. If it is in motion, it has kinetic energy. That energy is based off of 1/2 mv squared. So direction doesn't matter here, right? Kinetic energy is not a vector. So whether it's moving left or right, up or down, forward or backwards, the direction of the velocity does not matter in terms of the amount of energy that it possesses. So remember, if it's moving faster, it has more kinetic energy. If it's more massive, it has more kinetic energy. Your mass is a linear relationship, so if you double the mass, you double your kinetic energy, whereas your velocity is an exponential. So if you double your velocity, you have 4 times the amount of kinetic energy. Just remember that one. Now our gravitational potential, right, just to review this one as well from the previous unit, this is your stored amount of energy. When you see that word potential, bring it back to the idea that potential means that it can utilize that amount of energy, so it's stored. And the stored energy is dependent on the mass and its height above some arbitrary location. So the more massive the object is, the more gravitational potential energy it has, and that is linear as well. So double the mass, double the gravitational potential energy. Same thing goes for your height. If you are, some location above the ground and you triple that height off the ground, you're going to triple the gravitational potential energy that you currently have. We get a new one, right? And we get a new one here, and it's elastic potential energy, right? So this is now new from the previous unit. But before we truly get to the energy side of things, we're going to look at what's known as Hooke's law, which is the relationship with the amount of force that a spring is able to exert. If we go back to how we've done things earlier in the school year here, we started with forces, then moved into energies. So here we're going to take a little side note, look at Hooke's law, which is going to get us the forces behind the amount of energy that is possessed by some object that has elasticity. So we see our definition. The force created by a spring is in the opposite direction to and is directly proportional to the amount of stretch from its equilibrium position. So basically, here's what that means. If we put this into mathematical terms, your spring force, right? So the amount of force that is exerted by the spring is equal to negative kx, where k is the spring constant, and x is how far it is stretched or compressed in meters from its standard position. So breaking down the definition to the formula here, the force created by the spring is in the opposite direction. So if you notice, we have the force of the spring on the left side is positive. We are negative kx on the other side. Because if the spring is being stretched, so let's say I've got a slinky here, for example, right? And let's say we stretch the slinky. Well, if I stretch the slinky, that means that the force exerted by the spring is going to be inward, because when I let it go, it would snap back to its normal position. So we would say that I've stretched it outward, so the spring force would be inward. If I orient the slinky vertically, right, and I let some of this stretch a little bit, well, if I pull down on the slinky, we would say that x is downward, so the amount of force from the spring would be upward, because as I let it go, it's going to rebound upward. So as we see here, the spring force is always in the opposite direction of that stretch or compression from its equilibrium position. That's why we have that negative in there, because it's telling us that the spring force and the displacement, the stretch or compression that the spring it undergoes, are going to be opposite directions. Now, we need to have that negative here, right? Cannot emphasize that enough. Mathematically, it's going to help you understand the direction that the spring force is acting in comparison to the stretch or compression, right? It's going to always let you know it's in the opposite direction. Right, so note there again, negative sign is needed because the force is in the opposite direction as the displacement. That is important. Now the second part of that definition, seeing that it is proportional to the amount of stretch. So let's say I take the slinky and again orient it vertically. So here would be its standard length. If I stretch this, I don't know, 3 centimeters, that was more than 3 centimeters, and then I stretch it 9 centimeters, for example, right? At 3 centimeters, it's going to be some amount of force. And if I stretch it to 9 centimeters, it will then exert 3 times the amount of force because the displacement is 3 times greater. So the spring force would be 3 times greater. So whatever you do to that stretch or compression, right, that X value there, your spring force is going to respond accordingly. If you double the stretch or compression, you double the amount of force on the spring. If you have 5 times the amount of stretch or compression, you have 5 times the amount of force exerted by the spring. So if we practice this, originally a massless spring hangs vertically at a position of negative 3 centimeters from equilibrium with a mass of 0.1 kilograms attached to it. You then add another 0.2 kilograms to the spring. So to get a little visual on this, again, I'm going to go to the slinky here. So we orient the slinky. Notice how the slinky has some pretty definitive amount of stretch from where I'm holding it. It's going to stretch so far to its natural position. So negative 3 centimeters would mean that I've stretched it 3 centimeters down from equilibrium by adding that mass. I then add another 0.2 kilograms, which will make it stretch more. So the first question, how far will it now hang from its equilibrium position? The way that we would approach this would be utilizing Hooke's law, F equals negative kx, and looking at the weight that is being hung from the spring itself. So bringing back F equals mg, because the spring force, if we think about this, the spring force as this stretches down is pulling up. Right? It stretches down, the force has to be pulling back upward, but the weight is pulling it down. So the spring force is going to be equal and opposite to the weight that's hanging from it. Thus, we can set mg, the weight of the hanging mass, equal to negative kx because the spring force equals the weight. So our first situation, we have 0.1 kilograms, stretching it to negative 3 centimeters. Well, if we add another 0.2 kilograms, our total mass is now going to be 0.3 kilograms, which means, since we're going to be linear here, we're going to have triple the distance. So we've gone from 0.1 to 0.3 kilograms. Our mass is 3 times greater. Thus, the stretch is going to be 3 times greater as well. So it's going to be at negative 9 centimeters, or it is stretched 9 centimeters downward. The second question, how much upward force does the spring exert now? How we're going to look at this one, the spring force being equal and opposite to the weight. So F of the spring equals negative Fg, right? Opposite of the weight. We know it's 0.3 kilograms that's hanging there. We know G is negative 9.81 meters per second. So we take the product of those and we get 2.94 newtons. Again, emphasis here. Look at how that spring force came out positive. Spring force is positive 2.94 newtons. Our X value for the spring, that amount that it is stretched, is negative 9 centimeters. Spring force, opposite direction of our stretch or compression. Third bullet point here, what is the spring constant of this spring? So now we're going to go ahead and go F equals negative kx using Hooke's law. Rearrange that. We have our force of 2.94 newtons, and then we are over negative x, so negative times negative 0.090 meters to get 32.7 newtons per meter. And this is a great time to introduce fully what the idea of that spring constant is, right? What is K? What is a spring constant? That's telling you what the stiffness of that spring is. So the higher that value is, the more stiff that elastic material is going to be. The lower it is, the less stiff it's going to be, the easier it's going to be to get it to move. And really, when you look at the units on that as newtons per meter, you truly do get the breakdown on that. So newtons per meter tells you how many newtons of force you have to exert per meter to get that thing to stretch. So the bigger that value is, the more stiff that spring is. A shock in a car, for example, is going to be a very, very, very high value because those are very, very dense, thick coils that are hard to stretch and they're hard to compress, as opposed to the Slinky, right, which is very, right, this is much easier to move. You have to exert very little force to get this to stretch. A car shock supports an entire vehicle, right? There's a handful of them along the base of your car. They have to support the entire weight of that vehicle. So the better those shocks are, the higher that value is, the less your car's going to bounce up and down as you drive if it is a more stiff spring that's there. So that's your spring constant, how stiff that spring is going to be. Which then brings us here to our elastic potential energy. Right, so now it's the application of Hooke's law to the energy that it's going to contain as you stretch or compress that spring. And because it is storing that energy based on that stress or strain, this allows us to see that whether you stretch it or whether you compress it, both of them are going to store energy. It's just a matter of what it will do with that energy once it recoils. Our formula that we look at for our elastic potential energy in springs looks very similar in form to our kinetic energy, except here we're 1/2 kx squared. So notice, because it's x squared, whether that spring is stretched or compressed, that doesn't matter, because the amount of energy it stores is going to be equivalent whether an object is stretched 2 meters or whether it is compressed 2 meters. That 2 meters, the direction doesn't matter in terms of the energy that it stores. And again, K is going to be our spring constant measured in newtons per meter. So as we look at this here, right, we have our elastic potential energy. So if I take this Slinky and if I stretch it 10 centimeters, we'd be looking at 10 squared for our elastic potential. If I compress it 10 centimeters, we'd be looking at negative 10 squared, which is going to still get you, or negative 0.1 squared, which is going to still get you the same numerical value because the direction doesn't matter. And just kind of a good little side note here, it's the exact same as it is for work, because remember, work equals your change in energy. So the work that a spring does is equivalent to the elastic potential energy that it will possess. What you can really think about with the energy, if you stretch it, that energy is going to cause that spring to recoil back inward. And let's say you take a spring that's already stretched and you compress it down. When you release it, it's going to stretch back to its normal length. Any Nerf guns, right, that are spring powered work by this law. If you pull back on a rubber binder, the further back you pull it and go to snap it on somebody, the more painful it's going to be when it hits them. So our elastic potential energy practice here, you use a rubber strap to secure some cargo, and it is stretched 0.5 meters from equilibrium. If it has a spring constant of 88 newtons per meter, what is the stored energy in this system? So we'd be looking at our elastic potential energy of 1/2 kx squared, with our k value being 88 newtons per meter, and our x value is 0.5 meters, and that will be squared. So it would be 0.5 squared written in that formula. We have to have our stretch or compression be measured in meters. No other units. We have to be in meters. And this will get us to an answer of 11 joules. So a couple things to recall here. Hooke's law, F equals negative kx. Remember, your spring force is going to be in the opposite direction of your stretch or compression. So if you stretch, the force is directed inward. If you compress, the force is directed outward. And it's going to be a linear relationship. So if you double or triple the stretch or compression, you're going to double or triple the amount of spring force that the object contains. Our spring constant, remember, is how stiff that spring is. So the larger that K value is, the more force you would need to exert in order to get the object to stretch or compress. A lower K value means it's easier to stretch or compress that object. And then we bring it in terms of energy, 1/2 kx squared, where our elastic potential energy is going to be a direct relationship with K, and it's going to be a square with our x value, right? So if you double x, you have 4 times the potential energy. If you triple x, you have 9 times the elastic potential energy. So there we're looking at Hooke's law, our elastic potential energy, and a quick recap of the mechanical energy types studied thus far. Thanks, guys.